Hi everyone. In this video we are going to see the Coursera Digital Signal Processing Part 1 Basic Concepts and Algorithm Quiz 3 Solutions. Okay, let's take the quiz. The first question, write out the phase of the complex numbers A1, 1 minus j, and A2 is minus 1 minus j. Here you have the two complex numbers. They are asking what is the phase of these two. So for A plus IB complex number, phase is simply the tan inverse of B by A. Okay, let's see how it's. The first one, what the given is A1 is 1 minus j and A2 is minus 1 minus j. Now I am trying to represent on a complex plane. See, the x-axis is simply the real and the y-axis is imaginary. Let's take the every unit is 0.51, 1.52, and it is minus 0.5, minus 1, minus 1.5. Even the y-axis also I am taking is 0.5, 1, 1.5. The negative is also the same, minus 0.5, minus 1, minus 1.5. Now see the first one, 1 minus j. So real value is plus 1, the imaginary is minus. So the point is here, 1 minus j. Okay, so that seems to be like this. It seems to be like this. Now the angle you can evaluate in two ways, one in the clockwise direction, that, and the second is the angle. Okay, in the first one it is around the, see, this angle is okay, and the clockwise direction the angle is 315, which is the angle is 315 degrees. Okay, or you can represent the same thing in the anti-clockwise direction, which is the minus 45. Okay, now that is the phase of first one. The second is minus 1 minus j, that is the third coordinate. That is in the third coordinate. Now the curve is, that is seems to be like this. Okay, now angle is again in the two ways. The clockwise, the positive representation, that is 225 degrees, or you can evaluate the same thing with the negative, which is minus 135. So the phase of the second complex number is 225 or minus 135. So they clearly mention that the phase should be in the range of minus 180 to plus 180. So the phase of the first one is minus 45, which is in the specified range, and the second one is minus 135. Okay, so you need to write those two. The first one is minus 45 space minus 135. These are the phases of two complex numbers. Now the second one, let Twiddle factors, the w suffix n power k is e power minus j 2 pi by n k, and n is greater than 1, then w suffix n power n by 2 is equal to. Okay, let's see. Okay, let's see the given Twiddle factor, the w suffix n power k, what they define is my e power minus j 2 pi by n into k. and they given the n value is greater than 1. Okay, and they are asking to find the value w suffix n power n by 2. So simply the power is n by 2. So e power minus j 2 pi by n into the k values here is n by 2. So n and the 2 will get cancelled. Its value is only the e power minus j pi. E power minus j theta is cos theta minus j sin theta. So the cos pi value is minus 1. Okay, sin pi value is 0 simply. So its answer is minus 1. Okay. Next, the third one. Which of the following signals, continuous and discrete time, are periodic signals? Okay, that we can easily conclude by seeing the signal itself. X of n is equal to sin n I. Okay, so I already told you that to conclude any discrete time signal is a periodic or not, just check its frequency, whether it have the term pi, then it is period, otherwise aperiodic. So it is not the periodic one. Next, the continuous time signal x of t is t plus 2 pi whole square. It is continuously increasing function. It is not the periodic. Now the x of t is cos of 2 pi f naught t plus pi, which is the periodic. Okay, with the period is f naught. So the next one is x of n is minus 1 whole power n. Minus 1 whole power n. Now see this one. The signal is x of n is equal to minus 1 whole power n. When you are expanding this, or when you are writing as a sequence form, so I will start at n is equal to 0 onwards. Minus 1 whole power 0 is simply 1. Next, n is 1, it is minus 1. N is 2, 1. Then minus 1, then 1, then minus 1, then 1, and so on. Now see the amplitudes of the signal, or the signal x of n, which having the amplitudes 1, minus 1, 1, minus 1, 1, minus 1. So these two values, 1 and the minus 1, are continuously repeated. So it is a periodic signal. Okay. Now x of n is equal to minus 1 whole power n is a periodic. The next, x of t is equal to t minus floor of t. T minus floor of t. Okay, that is x of t is equal to t minus floor of t. Okay, the floor of t is nothing but that is round off to the lowest integer value. Okay, example, I will start from the t is equal to 0. We will check from t is equal to 0 to 1, then again from 1 to 2 we will set. Okay, now x of 0, simply it is 0 minus 0. Okay, the value is 0. Let us take x of 0.25. So it is 0.25 minus floor of 0.25 is 0 only. So its value is 0.25. Then x of 0.5. So it is 0.5 minus 0, it is 0.5. Next, similarly the x of, what is the 0.99 and like. So it is 0.99 minus, it is 0.99. When it reaches to the x of 1, 1 minus 1, 0. Now from 1 to 2, if you are taking the different values, so it is these values, let us say the x of 1.5. So it is 1.5 minus 1, the difference is 0.5. If it is you are taking the x of 1.999, so on, it is 1.99 minus 1, it is 0.99. Now observe the values, always these are varies from the 0 to 0.9999. Okay, that seems to be approximately a sawtooth function which increase the value from 0 to 0.999. Okay, and again the 1 to 2, then 2 to 3, like that. Now observe the waveform. Again it is the periodic. So x of t is equal to t minus floor of t is again periodic. So here there are the three periodic signals. One is x of t is equal to cos of 2 pi f naught t plus pi. X of n is equal to minus 1 whole power n. Then x of t is equal to t minus floor of t. Okay. The next one, Choose the correct statement from the choice below. If we apply the discrete Fourier transform twice to a signal x of n, we obtain the signal itself scaled by n, that is n into x of n. No, you won't get the same signal again. Okay, it's wrong. Consider the signal length n. Signal x of n is equal to minus 1 whole power n with capital N is even. Okay, then x of k is equal to 0 for all k except k is equal to n by 2. Okay, that we'll see. So given the x of n is equal to minus 1 whole power n and the capital N is even. Let the capital N value is 4. Okay, now your x of n becomes 1 minus 1 1 minus 1. I'm trying to find the x of k using the Twiddle factor matrix for 4 by 4 for n is equal to 4. The Twiddle factor matrix is first row is 4 ones, then the second row is 1 minus j minus 1 plus j, and the third row is 1 minus 1 1 minus 1, and next in the 1 j minus 1 minus j, which is multiplied with your sequence 1 minus 1 1 minus 1. Just do the matrix multiplication. The first one is first row. To complete the first row is multiplied with this your sequence x of n. Okay, now it is 1 minus 1 plus 1 minus 1. This is the first element. Okay, the second one is the second row is multiplied with this. So 1 into 1 1 minus j into minus 1, that is plus j, then minus 1 into plus 1, so minus 1, j into minus 1, it is minus j. Okay, the third element in the third row is multiplied with the sequence x of n. So 1 into 1 1 minus 1 into minus 1 plus 1 1 into 1 plus 1, next minus 1 into minus 1 again plus 1. Next the last element, the fourth element, that is fourth row, is multiplied with their sequence, that is 1 into 1 1 j into minus 1 minus j minus 1 into 1 minus 1 minus j into minus 1, it is plus j. Now the four elements are just observe these values. The first element is 0, second is also the 0, third is 4, the next is 0. Now that is, this is at k is equal to 0 and this is at the k is equal to 1, k is equal to 2 and k is equal to 3. So the sequence x of k is 0 for all values of k except k is equal to 2. That can be, this 2 I am writing as capital N by 2. So the discrete Fourier transform of x of n, which is minus 1 whole power n for even values of n, it is 0 for all values of k except k is equal to n by 2. Okay, so that is, the second answer is right. And see the third one. Consider the length capital N, signal x of n is cos of 2 pi n ln plus pi, where capital N is even, again the L value is n by 2, then x of k. Okay, now says, let's see the given sequence x of n is cos of 2 pi by n ln plus pi, and the given condition is the capital N is even and capital L is n by 2. Now simply substitute the L value in this. It is 2 pi by capital N into capital N by 2 into small n plus pi. So capital N will get cancelled and the 2 is also get cancelled, that is cos of n pi plus pi. So write this the cos of n pi plus pi, that you can write as e power j pi into e power j n pi plus e power minus j pi into e power minus j n pi by 2. So here you can write as e power j pi, e power j n pi value is minus 1 whole power n plus e power minus j pi. You can write as e power minus j n pi is also values minus 1 whole power n, that is divided by 2. So that is, so you can take the minus 1 whole power n by 2 is common, that is e power j pi plus e power minus j pi. So which is e power j pi plus e power minus j pi divided by 2, which is cos pi minus 1 whole power n. This is your signal x of n. So apply the Fourier transform for this using the previous derivation, which is cos pi into capital N only at k is equal to n by 2, and its value is 0. K is not equal to n by 2. Just now we seen that the Fourier transform of minus 1 whole power n, its value is 0 for all values of k except k is n by 2. Okay, at k is equal to n by 2, its value is capital N. So capital N into cos pi at k is equal to n by 2, and it is 0 for remaining all the values. Okay. Now see the option. They given it is n by 2 into e power j pi, so it's wrong. Only the one answer is right. Next, fifth one. Consider the Fourier basis, the Twiddle factor w of k, where the Twiddle factor w of n is e power minus j 2 pi by n in k from 0 to n minus 1. Select the correct statement below. So here they are finding the inner product of Twiddle factors. Okay, that's in. So I'm taking the Twiddle factors wi and the wj. So this I'm evaluating by taking the capital N value is 4, and let us say the I value is 0 first. So that means that is w of 0, which is the vector on 1 1 1. Okay, now let's say j value is 1, so 1 is the vector and the elements 1 minus j minus 1 and plus j. So the inner product for different values 1 1 1 1 is multiplied with the 1 minus j minus 1 plus j. You know the inner product is nothing but the sum of products, that is 1 minus j minus 1 plus j. Its value is 0 where I is not equal to j. Let us say the I is equal to j, so the both are equal 1 1 1 1 and again the 1 1 1 1. So the answer is 4, which is equal to the capital N. So for this, the I is equal to j, the inner product is capital N, otherwise it is 0, the second one. Okay, now see the sixth one. See the sixth one. Here you have the three signals. One is a blue color signal, and one second is a green color, and third is a red color. Just observe the blue color, which is a cos signal. Okay, and how many cycles we have? Just see, check it here. 1 2 3 4. Okay, we have the 4 cycle over the period from 0 to 60, or nothing but n is equal to 64. Okay, now the green is how many cycles? 1 2 3 4 5 6 7 8. We have the 8 cycles over the same range. Okay, so since it is starting with from the 0, so this green color is nothing but the sinusoidal signal, and the blue color is a cos signal, and the red color here, the third signal, is simply having the constant amplitude. Simply it is 1. It is a signal. Okay, now how the three signal? The y1 is a blue, which is a cos signal. Y2 is green, which is the sinusoidal signal, having the amplitude is 0.5, and the y3 is red, which is the DC, having the amplitude is 1. Sum of all these three is x of n. So they are asking the y2, y1, y3. So the discrete Fourier transform of these three. Okay. Now see the first one, y1 of n. Its amplitude is 2 cos of 2 pi by capital N. The capital N is the 64 samples into how many cycles it is having? Only 4. So 4 into n. 4 into n. Okay. Now the discrete Fourier transform simply you can write as capital Y1 of k, which is the inner product of W64 of n comma Y1 of n. Okay, so this I am writing as, for this the so see the I am going to simplify the Y1 of n little bit more. So it is cos theta form. So I am writing as an exponential. So 2 into e power j 2 pi by 64 into 4n plus e power minus j 2 pi by 64 into 4n. So divided by 2. This 2 will get cancelled. Now see this one. Here the W suffix k of n, what the given is e power j 2 pi by n and k. So this I am writing as e power j 2 pi by n 4 into n. So I am writing this as 64. The n value is 64 power 4. Okay, power 4 of n. Okay, plus here we have the negative term, so that I am writing as e power j 2 pi by 64. This is minus 4 into n. So I will explain that again. So W4 of n plus, okay, this e power j 2 pi by 64, since the Twiddle factor is a periodic, so it can be written as capital N minus 4 into n. So now it is W suffix W4 of n plus here n value is a 64 minus 4, it is 60. So 60 of n. So now your Y1 of n is Twiddle factor power 4 of n plus Twiddle factor power of 60 of n. Now the Y1 of k is inner product. Let us say this is I for all I values. 4 of n plus W power 60 of n. So just now we seen that the inner product of 12 factor values is equal to the capital N when the powers are equal, otherwise simply 0. So here the first one is W power I of n, where I range from 0 to 63. Second one is W of power 4 of n. So when I perform the inner product, when I is equal to 4, then only this product is capital N, otherwise it is 0. That means this value is equal to the capital N, nothing but the 64 at k is equal to 4. Okay, this you can write as a k also, no problem, where the k is ranging from 0 to 63. Okay, and the second one is W power k of n, the inner product with W of 60 of n. Again, these two terms, inner product is non-zero only at k is equal to 60. Again, value is 64 at k is equal to 60. Okay, and it is 0 else. It is 0 else. This is Y1 of k. Okay. So in the same manner, see the Y2 of n. At the Y2 of n is amplitude is 0, 1 by 2 sine of 2 pi by 64. We have the 8 cycles, so 8 into n. So write in terms of exponential. Now it is 1 by 4 j e power j 2 pi by 64 8n minus e power minus j 2 pi by 64 8n. Okay, it is 1 by 4j. This you can write as w Twiddle factor power 8 of n, where the k value is 8 here, minus here the Twiddle factor power, or the minus 8, that is 64 minus 8, so which is simply 56 of n. Okay, now see the y2 of k, that is the Fourier transform of y2 of n, is again the inner product between the w power k of n and 1 by 4j w power 8 of n minus w power 56 of n. So this having the two terms, one is the inner product between the w power k of n with the first term, and again the inner product between the w power k of n with the second term. The first one, it is 1 by 4j into capital N value 64, only at k is equal to 8. Only at k is equal to 8, and its value is again have one more non-zero value, that is because of the second inner product. Its value is minus 1 by 4j. So simply have here the minus and 1 by 4j into 64, that is at k is equal to 56. K is equal to at 56. Now see 64 by 4j, which value is a minus, which value is minus 16j, which is at k is equal to 8. Okay, then the minus 64 by 4j, its value is plus 16j at k is equal to 56. Okay, and this is at the second one. And the third one, again the y3 of n is simply the one where n is equal to 0 to 63. So once you are applying the discrete Fourier transform, its value is 64 into del of k. Okay, now see the values. Y2 of k is 16j, 16j, both are positive. No, one is positive, second is negative. And second one is norm square, the power is not equal to the 12,500. You can evaluate this. And the y3 of k is 64 for k is equal to 0, otherwise 0. Just see the y3 of k 64 del of k. This exists only at k is equal to 0, value 64, the remaining it is simply 0. So third one is right. And the fourth one, y1 of k value is 2 for k is equal to 4 and 16. No, its value is 64. So only the one is right. Next, seventh one, consider the length capital N signal x of n is equal to cos of 2 pi L by mn by n, where m and L are integer parameter with 0 to n minus 1 or 0 to m. Okay, choose the correct statement among the choice below. The first one, consider the circularly shifted signal y of n is equal to x of n minus t. Okay, in the Fourier transform, since the DFT operator is a shift invariant, it is y of k is equal to x of k using the time shifting property of the discrete Fourier transform. So the Fourier transform of x of n minus d circular shifted, its value is x of k into e power minus j 2 pi k d by capital N. So the y of k value should be x of k into e power minus j 2 pi k d by n, but again both are equal, so the first one is wrong. So if n is equal to m and n is not equal to 12, it is easier to compute norm for this using the partial identity. It's right. The signal is always having the always exactly the L period from 0 to n. It is not always, it is only at capital N is equal to m and n is not equal to 2l. In that case only it having exactly the L periods. Okay, and the next one is the DFT x of k has two elements different from 0 if n is equal to m and n is not equal to 2l. So here they given the small l. I think I'm thinking it's a printing mistake. It is 2 into capital L. In such case, it is correct. Okay. Next one. Consider an orthogonal basis by select the statements that hold for any vector x. So norm square values, that is 1 by p 0 to n minus 1 x by I. Okay, this is when the norm square of pi I should be p. But here again only the norm, it should be the norm square. Okay, so that given the third option. Okay, at the same time, see the second one here, there is no multiplication factor, so the norm should be the 1. It is right. The second and the third are correct. And the ninth one, pick the correct sentences among the following ones regarding the DFT, capital X of a signal, small x of length capital N, where capital N is odd. Okay, so Hermitian symmetry x of 0, this x of n is equal to x of n minus n complex conjugate. For n is equal to 1 to n minus 1, Hermitian antisymmetry is x of n is equal to minus x complex conjugate of x of n minus capital N. So the discrete Fourier transform of Hermitian symmetry is always be the real signal, that we already studied that. Okay, one of the DFT property is the discrete Fourier transform of the Hermitian symmetry is the real, and the discrete Fourier transform of Hermitian antisymmetry is purely imaginary. If signal x is a Hermitian symmetry, then the DFT is real. If the signal x is a Hermitian antisymmetry, x is purely imaginary. If the signal x is purely real, it is not purely imaginary. We did a lot of problems on discrete Fourier transform. So it's a combination of both real and imaginary. If the signal x is a Hermitian symmetry, DFT is also the Hermitian symmetry. So DFT is a purely real number. Okay. Now we'll see the answers by submitting the form. Okay, 100%. Thank you for watching.